Hi, this series of lecture will be on eccentric loading of columns. And similar like bending, you have centric bending and eccentric bending, and this one we have eccentric loading. Right, so when you see the eccentric bending, what you tend to observe is when the load is applied, the axial load is not applied. Okay, so axial load is not acting on the centroid axis. Like what you see over here, right, on this slope P is offset by a distance E. So when that's the case, what will happen? Okay, so when that's the case, you have a load coming down on the and this is analyzed as a load coming down along the centroid P, and then you have a moment which is P multiplied by E. So how the structure will buckle, or the columns will buckle in the same way like before, but now you have extra load. Okay, yeah, extra moment, which is your PE. Okay, and then later we will break it down into at the midpoint what's going to happen, or at a certain distance from along the x-axis. So from here, as usual, if this is our transformation x, and that's our transformation y, so this is our y and this is our x, we have two boundaries now. Okay, so boundary condition when x is equal to 0, y is equal to 0, and x is equal to L, y is equal to... So the analysis with centric loading is still the same. Okay, now we're going to pick a certain distance x from the top point A, okay, and we're going to call this point Q. Right, at this moment I want you all to ignore this moment down here. Okay, it's not valid. So the moment at point Q will be equal to PE. Okay, so it will be PY. Y minus is acting in a clockwise direction, minus by PE. So the PE is of the centroid distance, okay, over here, and it's also rotating in a clockwise direction. Then as usual, we apply the elastic curve theory. So when we apply the elastic curve theory, it's this term that we see. Okay, so this is elastic curve, right? So then you equate everything out, then you have the expression over here, right? And then we're going to let small p squared is equal to p over ei, and then we rewrite equation 2, we get equation 3. Okay, and then from then on we have a general solution for complex conjugate roots. That's not homogeneous equation, because the entire term over here is not equal to 0. It's not equal, so it's not homogeneous. So we have an approximation general solution, which is a sine px plus by b cos px minus e. E over here again is the offset distance where the axial load is applied. That's where our E is. Okay. Then from here we put in our boundary condition. When x is equal to 0, y equals 0, we have b is equal to E. And then the next one, when x equal to L, y equal to 0, and the next boundary condition, we have our expression in equation 5. Okay. Then we start applying double angle. Okay, so we know that sine 2 theta is equal to 2 sine theta cos theta, and as we let 2 theta is equal to PL, we get theta is equal to PL over 2. Okay, then from here we have sine PL, okay, is equal to 2 sine PL over 2 divided by cos pi. Then note we have another expression where cos 2 theta is equal to 1 minus 2 sine squared theta. Okay, so we substitute theta with 2 theta equal to PL, so we have this expression, and then we have expression equation number 8. Then why are we doing this? Because we know, right, this equation over here, a sine PL and cos PL, we can use double angle to express it into a not simplified but a different expression. Okay, so from here we substitute equation 7 and 8 into 5. Okay, so we get our A to be E tangent PL over 2. So this will simplify, using the double angle will simplify our expression A. So expression A, what is expression A? Expression A is a constant over here. So from here, we substitute A into our yx function, and then we get this expression, and then we have our equation number 9. So yx, so we have our, so where we are is over here. Okay, so we have we use, okay, so this is the same expression over here, and we simplify it then. Now y max will occur at x equal to L over 2. So at the mixed span, so we know that we have our load over here. This is our distance L, right? When the structure buckle, right? And then with respect to our centroid, this will be known as our y max. So we know that the y max will occur at L over 2. Then equation 9, okay, in terms of y max, initially we have it as y, now it's y max. You have this expression over here. And then from equation 9, you can see the math is pretty straightforward. You get equation 9a, where y max is equal to E secant PL over 2 minus 1, and multiplied by the whole thing, multiplied by the E, which is the offset distance. Okay. Then we have our y max is equal to E or secant square root of P over EL square root multiply L over 2 secant minus 1, and the whole thing multiplied by E. So that's our 9b. So from 9b, to get y max, when y max tends to become infinity. Okay, so y max tends to become infinity is when 1 over cosine over here or secant over here go into what? Infinity, where you will see your what? Y max. Okay, so we have critical load now. So now the load, rather than P, is our critical load by EL. You have this expression. Then we have our EI expressed in P critical load L squared minus pi squared. And then we substitute equation 10 to equation 9b. This is our y max in terms of, to get our y max value. The expression before that you have over here, right? And the expression we get now is in terms of the critical load. Now for eccentric load, okay, so now we have find our y max. But most of the time when we design our structure, it's not just looking at y max. So what if its deflection is the maximum? You want to know the what? The stress. Okay, you want to know what's the maximum stress. So for eccentric load in bending, right, you have P over A plus by my, okay, over I, where C is the maximum y value, where C is equal to y max. Okay, not what? Okay, y max. So C over here. So if you have, if this is your axis y, right, this is your C value, and this is the cross-sectional area. So there's your C. Okay, I don't want to confuse you guys. Then y max is equal to P y max. Sorry, moment max is equal to P y max plus by PE, right? Where P goes. So what this means over here is this. Right, so you have your P offset, right? You have your P offset. So one of the moment is contributed by E, and the other one is contributed by what? Y max. Okay, right, when it's buckling, right? So you have your stress max is equal to P over E plus by this expression right here, and then you can rewrite the expression in this form. And then we're going to substitute I equal AR squared. And then finally, you have this expression over here, which I'm going to call it equation number 11. Where you have stress max equal P over A. Okay, I mean, you have your equation 11 expression. So from here, you're going to use a table, okay, which will be that we can get from Materials Handbook in terms of buckling. And you have to use this table, and this table or these graphs or these figures is acquired from experimental work, and this is specifically for yield strength of 250, Young's modulus 200. You have to find your LE over R, you have to find your EC over R squared, Okay, E is the offset, C is the maximum distance from the neutral axis, R is your radius of gyration, and then you find your PC over R squared, you have your LE over R, then you find your critical load over A. As I said, this graph is acquired from experiment. Okay, then for small value of L over R ratio, if your L over R ratio is very small, you can simplify your expression into stress max is equal to PA bracket 1 plus by offset distance divided by maximum distance of the centroid divided by radius of gyration. Okay, so this is the how we're going to analyze structure that has gone through eccentric loading. Okay, and this expression is important. So this expression is important. Okay, we're going to do one example now. Right. So in this example, the steel column, right? The steel column support two eccentric load, 120 millimeters by 80 millimeters at 130 kilonewton and 50 kilonewton. It's assumed that the top is pinned at its top and it's fixed at the bottom. Okay, and we're going to determine the maximum stress of the column and maximum deflection and maximum stress in the column. Okay, so we have these two what we have to determine. So the equation that we're going to use is stress max is equal to PA. Okay, so it's our stress max equation and our Y max equation. So the first thing we do, we have to find out that buckling. So if you look over here, buckling will rotate, will buckle on the x-axis, right? So if this is our x-axis, so if we have our expression over here, this will be our y, this will be our z, and over here this will be our x. So the buckle will buckle this way, so you'll buckle along our x-axis, right? You'll buckle this way. So when that's the case, we declare that buckling will occur about the x-axis. Straightforward. Okay, and then from here you have to find out Ixx. So Ixx over here, you know that this is your width, and this over here will be our depth. So we're going to take it as a solid first. So solid is B is a rectangular 0.12 cube over 12 minus by twice the two holes to make the I, the width, and then the depth over 12, and then we have our Ixx to be equal to 6.9 times 10 to the power minus 6 meter 4. Okay, and then so we have our I, then we need to find our area. So area will be equal to twice of 0.1 multiplied by 0.12 and then plus by the web section of it, 0.1 multiplied by 0.01, and this we get 3 times 10 to the power minus 3 meters squared. So from here we need to find R. Here we need to find, okay, so from here we can find R, which corresponds to the radius of gyration. Where we have the expression is I is equal to AR squared. So R is equal to square root I over A. So it will be equal to I 6.9 times 10 to the power minus 6. Area is 3 times 10 to the power minus 3. So this will be equal to 6.9 divided by 3 times and it's equal to 0.04796. Okay, 0.04796. Okay. That's our radius of gyration. So we know that our from the configuration of our structure, okay, of the structure, where one end is fixed and the other is pinned, right? So when we see that, we go into week 13, right? One end fixed, one end pinned. LE is equal to what? 0.07 L. So from here, we know that LE is equal to 0.7 L, and this will be equal to 0.7 multiplied by L, which is 6, and this is equal to 4.2 meters. Okay, so that's our LE. So from here, we can calculate our critical load, right? So we know we can calculate our critical. So we calculate our critical load with this formula over here. Right? So the critical load, so this will be equal to pi squared divided by L squared, 200 times 10 to the power 9, and then we found that our second moment of area is 6.9 times 10 to the power minus 6. So from here, our critical load is pi squared, 4 squared, 200 times 10 to the power times is 772.112 times 10 to the power 3 Newton. Okay. Then next, we're going to calculate our force, P. So we have one load coming in at 130, and the other load is 50. So P, the applied load, is equal to 130 times 10 to the power 3 plus by 50 times 10 to the power 3. This will be equal to 180 times 10 to the power 3 Newton. Okay. Next, we have to find our offset. Okay, so to get our offset, I'm going to sketch the top part of our structure regarding the load. So this is the top part, okay? And then over here we have our centroid. We have two loads applying. One is at 100, one's at 50, and the other one is at 130. Okay, so we know that this is 50, and then the next one is at 130. So we know that this load is 50 times 10 to the power 3, and the other one is 130 times 10 to the power 3 Newton. And then we also know the respective distance. So this is 120 millimeters, and this is equal to 80 millimeters. So over here, 0.12 meters, 0.08 meters, right? So from here then, now you might be wondering, Eugene, what are you drawing over there? Okay, so you see over there, so what we are sketching is up here. Okay, so what I'm sketching is up here. I know it's not exactly the same look, but okay, I'm trying to. Okay, so from here we know, based on the distance and the forces, we know the moment will be in this direction, right? We know that this is our moment, and a moment, yep, that's our moment. So moment, right, that moment over there will be equal to 130 times 10 to the power 3, right, multiplied by 0.12 minus by 50 times 10 to the power 3 multiplied by 0.08. And moment, we know that is P multiplied by E, and then this will be equal to 116.00 And then E will be equal to 11600 divided by P is 180 times 10 to the power 3. So we know that the offset distance of E is equal to 64.444 times 10 to the power minus 3 meters. Okay. So from here, we know that we're going to use this expression over here now. We're going to apply this formula. Once you have done the analysis, it's all just plugging in formulas. Okay, the formula is this formula we're going to apply. Stress max. So we know that P, so now it's about plugging in formula. 180 times 10 to the power 3 divided by area. 3 times 10 to the power minus 3. 1 plus by E. We found all this, by the way, right? 0.444 times 10 to the power minus 3. C is equal to 0.06. Now, why C is equal to 0.06 is because IYY and then IXX, and this is our C value. So this is equal to 0.12 divided by 2. Right, so that's why it's 0.06. Then we have our R squared. So divide by R squared over here. So it's equal to 0.04796. Right, 4796. Okay, 0.04796 squared, and then this thing will have a secant pi over 2, and then square root of 180 times 10 to the power 3 divided by the critical load 772.112 times 10 to the power 3, close bracket, and this term will be equal to 60 times 10 to the power 6 multiplied by 1 plus by 1.6801 and then multiply by 1.37757, right, or square brackets. So over here you found that the maximum stress, which is 199 times 10 to the power 9 times 10 to the power 6 Pascal. So therefore stress max is less than the value of the maximum allowable stress of EU of 360 times 10 to the power 6. Okay, so structure will not yield. Okay, the structure will not yield. And the next thing that we're going to calculate is the Y. Does not mean it's not, it will not yield, will be fine, right? We also want to know what is our Y max. How much is our buckle over a 6 meter structure? Okay, so you want to know that, right? Physically, you know it will not fail, but it will deflect a bit. You have to, like, if it's seeable to the naked eye, it's dangerous. Imagine your structure and there's a load coming down and you can see it bending, you'll start to panic. So you have to know what's your Y max, right? So we're going to calculate Y max. Oh, by the way, you have to remember when we are calculating these terms over here, you have to make sure that it's in radians. Okay, you don't put in degree, you put in degree, especially when you have pi over here, make sure it's in radian. Okay, if you have it in degree, oopsie a daisy. Then from here, we're going to find our Y max. So our Y max value, right? So this is, so it's just again putting in formula 64.444 times 10 to the power minus 3. Then we have secant, the whole thing square root of 180 times 10 to the power 3 divided by 200 times 10 to the power 9, 6.9 times 10 to the power minus 6, you close bracket, and then over here you have 4.2 divided by 2, and then you minus 1 again. Okay, so over here you will have 64.444 times 10 to the power minus 3, and then this expression over here, so this expression will be 180 or square root of 180 power 3 divided by 200 power 9 divided by 6.9 power minus 6, close bracket. Okay, then cos, right, then 1 divided by times by 4.2 divided by 2. Okay, so this will be equal to 1.3775. Okay, and then this will be equal to 0.0243 meters. Let me do it again. Okay, so it's square root 180 power 3 divided by 200 power 9 divided by power minus 6 times 4.2 divided by 2, cosine 1 divided by minus 1. Okay, sorry, there's a minus 1 down here. My bad. Okay, so it's 0.3775 multiplied by 64.444 power minus 3. So 0. So you also again have to make sure that this is in what? When you calculate, is in what? Radians. Okay, so this is how we calculate. It's just a formula that we have to plug in. I went to the point to how that formula is derived. Okay, to calculate our Y max and our deflection. I'll come back again, and then we're going to use this chart, okay, to analyze our structure. Thank you.